Okay, thank you, and welcome to my talk, Fraunhofer IMS, your sensing partner for Lab to Fab. First of all, I want to introduce ourselves. Sorry. A little bit. So we are part of the Fraunhofer Gesellschaft, so we are all over Germany, more than 70 institutes. Our institute is located here in Duisburg, in West Germany. And we are part of the Research Fab Microelectronics Germany, FMD, so where all of the microelectronic institutes are combined to one-stop shop. Our institute is separated in 5 business units: in health, industry, mobility, space and security, and silicon solutions. And we have 4 core competences: embedded software and AI, smart sensor systems, technology, and center for technology. So today I want to focus on my business unit. It's the business unit Silicon Solutions. So we are dealing with all customer requests which which are dealing with our clean room. So in our house we have an own 200 millimeter clean room, so where we are focusing on post CMOS processes, and therefore on the other hand the core competences, technology and center for sensor technology are working on these applications. So what kind of technologies do we provide? So we have, for example, CMOS-based technologies for optical sensors, so from X-ray to near-infrared. We have several MEMS processors like pressure sensors, but also gas sensors or also acceleration sensors. We have a big field of photonic integrated circuits, which are combined on a CMOS wafer. We have the field of functionalized carbon nanotubes for also biomedical sensing, and we are in the field of material development. So what do we provide in general? So we can start with any kind of simulation of the process or of the device. We are doing the design, the layout. So for the devices and the sensors, then we can also fabricate them in our clean room, starting with the first development. We are reaching in demonstrator, but also up to a pilot series. And when the wafer or the chips are ready, we can also characterize them in a wafer test or also in a parameter tester. Where do we do our technology? As mentioned, we have an own clean room. So it's a 0.35 micron MEMS and up to process clean room. We can start on any kind of substrate. So we can start on a blank silicon wafer, but we can also start on any kind of CMOS wafer, for example, in some cases also on glass wafers. We have, or nearly all of our tools are automated, so we have an automatic handling systems, and here, as already mentioned, from demonstrator to prototype. Here are also some facts on our clean room. So actually we have a 1,600 square meter clean room separated in ISO 4 clean room and an ISO 6 clean room. We have a 200 millimeter or 8-inch cassette to cassette handling, so mainly on silicon wafers. In some cases also glass wafers are possible. We have the combination of internal and external services, so we can also provide, especially during the FMD, we can change the wafer. So if there are any processes which we cannot deal with, we can also use other institutes or other suppliers for doing so. We are using a manufacturing executive system, so this helps us to have a good overview what was going on with the wafer and even with each chip. This also includes checklists for our tools, for example, so that we are always sure that our tools are working as we expect that they are working. And last but not least, we are ISO 9001 certified. So in the past, we had several industrial projects or cooperations And two examples are listed here. So for example, we had a big cooperation with Elmos Automotive, and there we developed the L035 CMOS process. We had also a big cooperation with Infineon, where we also developed the 1200 volt SOI driver processors. Yeah, we have lots of experience in upgrading processes. So actually we are cooperating with 3 startups. So this means the startups comes to us with some kind of demonstrator in a really small scale. And now we are helping them to scale them up to 200 millimeter wafers, and also up to 1,000 wafer per year. Fraunhofer IMS is also part of the APEX pilot line, so which goes all over Europe, and there also the focus is on the simplifying integration of processes, and also making innovative technologies accessible for industry and also for smaller companies. To have a feeling what does it mean to scale up, so how many wafers do we measure? So we had an example here for a backside illuminated CSPET process. So this process was upscaled up to a prototype series. Here are some information listed. So our SPETs were at least 5 times, or had at least 5 times a higher fill factor, allows a high resolution seed SPET array, and there were separated wafer processing. So on the right hand side, a short image of these chips or these wafers are shown. And here are some data of our chips. So we measured more than 20,000 chips in total, which means more than 275 wafers to get a good statistic all over our process and also over our devices, so how they are working in the end. So how do we come to these results? So what do we use or what kind of processes do we use? So in our clean room, we are covering more or less the full process chain, starting with different deposition methods like CVD, PVD. We have lithography. We have also DPUV lithography, deep reactive ion etching to get really high aspect ratios in our silicon substrate. We have the field of atomic layer deposition, of depositing really thin layers. We have several etching tools available, chemical etching, but also physical etching, HF etching, for example, and also our patented sacrificial layer etching process to create freestanding structures. We have the field of 3D integration, so this means we have several or 2 wafers, so which are then integrated by micro wires. I will come to it later on. And as also mentioned, we have metrology, so this means inline metrology for testing our single process steps, but also the test capabilities when the wafer is ready. So parameter test, but also really wafer test when we want to test the device itself. So now I come to some examples where we used or we're actually using all these parts of technology or how we combine them. So this 2.5D and 3D integration is one part. So here we have the possibility to have any kind of readout wafer. So this could be in Fraunhofer internal readout wafer, but it could also be a wafer from X-FAB or a tower or wherever. And then we have our MEMS wafer on top, and we can combine them by wafer-to-wafer bonding. And then we are doing the interconnections through silicon vias. So there we are etching from the top wafer down to the bottom wafer to get the contacts. And here we are using especially our ALD technology to get a really good contact from the top wafer to the bottom wafer. So this technology is used for the CSPETs, as mentioned in the beginning of my talk. So these wafers are combined in this way. So there we are using the through silicon wafers. Another example where we are using these combined sensors or these combined wafers for our microbolometer. So here we are in the long wave infrared sensors, but we have also a mid-wave infrared sensor, so that we have the chance to combine different specifications here. Another project or another application are the terahertz tags. So here you can see also an 8-inch wafer, and there we used our etching tool for etching really through the whole wafer, so that we can separate these tags. And this technology can also be used if you have some special sensors which are maybe very sensitive concerning vibrations or something like this, so that you are not able to use a standard screw-up process. Then you could also use this process for dicing, so for separating the single chips. Another sensor system is, or we are also in the biomems sensor application. So this sensor was also a cooperative project where we developed a sensor system which was especially for the RS virus, for detection of this RS virus in an POC. And I think in the last years this becomes more and more important, because especially for small babies, this RS virus is really hard, so it's really dangerous. So we tried to test it early to come over it. We have a long history in post-CMOS pressure sensors, especially for medical devices. This area started in 2004 with a brain pressure. So we developed a brain pressure which was for hydrocephalus patients, and this pressure was really implanted into humans. Same for an eye pressure system. So this was for glaucoma patients. So this was also or is also implanted into several patients. And the development goes on. So we also developed a blood pressure system or a heart pressure system. And this is an ongoing research field. So here we are improving more and more our pressure sensor process, so we can have a deeper look inside it. So this process is also a monolithic integration onto a CMOS technology. So here we really start on a CMOS wafer, and then we are producing our process on top of this wafer. So no bonding, but really processing on top of this CMOS wafer. You can see it's a capacitive sensor. You can see the membrane on top of it. There also an ALD layer was used. And these sensor systems are drift-free and really long-term stable, which is a good advantage or a need for implantable pressure sensors, because you do not want to change the pressure, the sensor after a few months. But so this needs to be inside the brain for several years. And the specialty here is that the pressure range itself is tunable by the design. So the range of the pressure sensor depends on the diameter of the membrane, and I mean this is easily adjustable by another layout, but it doesn't affect so much the process itself. Okay, we also have an 8-inch pilot line for post-CMOS photonics at IMS. So these activity started, I would say, around 5 years ago. This is also one big part in the APEX pilot line. And here we are also covering the whole process line. So we can do the design and layout. We can simulate the photonics. Then we can also produce them in our clean room, and we also have the possibility of characterization, so of electrical and of optical characterization. So Our photonics is a silicon nitride, mainly silicon nitride based. We also have some waveguide materials like tantalum pentoxide or aluminum nitride. And here we also can start on a blank wafer, but we can also combine these peaks with CMOS ASIC. So there we could also start on any kind of CMOS wafer. Then we need to do some kind of planarization, and then we can do our post-CMOS integration by producing our waveguides on top of these wafers. So here are some typical wavelengths where the for different applications. So starting with around here 400 nanometer up to 3 microns, or here 1,550 nanometer. In our institute, we have several ALD tools, atomic layer deposition. So the benefit of ALD is that this process is very homogeneous and that it covers really everything. So a very high conformity. And this research field shows very good our lab to fab approach. So we can start here on the development side. We have a really small manual loaded tool. So this gives us a chance to develop new ALD processes. So here we are starting with the new processes, testing, okay, is it feasible or not? If it gives us good results, then we can go to our so-called single ALD. Excuse me. It's a two-chamber cluster system with automatic handling. One chamber is the thermal chamber, and one is a plasma-enhanced chamber. And so here we have, of course, a higher throughput than at our mini ALD. If the throughput increases more, then we can also use our batch system. So here we have the possibility to coat up to 25 wafers at the same time, which is, of course, a great advantage concerning the time, because ALD is a very slow process. So just to give you an idea, but for, I would say, 50 nanometers of aluminum oxide, we would need around 3 hours. So if you want to process 25 wafers, then you would need to, 25 mal 3 hours, so it's a time-consuming process. But here we have the chance for some standard materials and also for ruthenium to decrease the time by depositing it in just one step. Okay, last but not least, we also have our fast ALD. So this is a combined system. So it's a mixture between ALD and CVD to combine both benefits. So to increase the time a little bit, but maybe by losing a little bit of homogeneity. But in some cases, this is okay. And so this is also a chance to accelerate the process and to get higher volume by using ALD. We do not only develop the processes itself, but we have also a strong cooperation with the IFW in Dresden, with Professor Anjana Devi, and there they are developing precursors itself. So there they are working on precursors to tune them for the best specifications for special or for the best specifications for any applications. And so once they have developed it on a really small coupon, then we have the possibility to get them into our clean room and to scale up these new, not commercial available processes also on an 8-inch wafer. So of course you cannot read all the materials, but this should just give you an idea on how many materials are available at the moment at our institute, but we are always interested in developing new materials. So if there are any needs to some special other materials, so there are other possibilities to get also new materials into our clean room. So where do we use ALD? This is our sacrificial layer technology, which I already mentioned in the beginning. So how does it work? So we start also on a substrate, then we deposit a sacrificial layer. We are etching holes, for example, into the layer or what else of structure we want to produce. Then we deposit ALD, and because of the high conformity, ALD goes to the surface, but also inside all of these holes. Then we are etching the surface so that there is no ALD left. And then in the last step, we are etching, or we are using isotropic etching for removing the sacrificial layer, and only the ALD structures are left. So on the right-hand side, you see two examples. So in the top, you see some kind of membrane, which could, for example, be used as some kind of capacitor. And you also see on the bottom nanoneedles, which were produced by ALD. These nanoneedles were used for penetrating single cells. And if we combine these needles, for example, with a fluidic system underneath, we have the opportunity to bring some fluids into the cell, or also to extract some fluids out of the cell for analyzing. And if these needles are out of a conductive material, then we also have the possibility to get the electrical information out of the cell. We used it also for, or these layers can also be used as sensing layers, because they are really, really thin. They have a high sensitivity. Here in this example, we built a gas sensor. So we have these nanowires out of a thin oxide above a Richter structure, and we checked them. So if gas is on side of the surface, the resistivity changes, and we checked these sensors against a reference sensor, which is shown on the bottom. And here on the top, you see the incoming gas. And here the reaction of the sensor. So in black it's the reference sensor, in blue and red are our demonstrators. And one can see that the reaction time is as fast as for the reference sensor, but this sensor was specially designed for NO2 detection, and lots of the reference sensors have the disadvantage that there are cross sensitivities, as are shown here. So here in green there is the NH2 inlet, and you see from the reference sensor a little peak. So there is a reactance through this other gas, and for our demonstrators, so there was no cross content or cross sensitivity towards NH3, and also not towards CO. Here are some pictures, what we have designed with this sacrificial layer etching. Here on the top there are the gas sensors, and here it was also used in a double way. So we have freestanding heater structure, and above this freestanding heater structure we had this freestanding nanowire. With ALD, we have also the chance to deposit 2D materials. So the benefits are the high sensitivity, the strong reaction to surface change, the low limit of detection. So we can detect really, really small parts of biological material, and of the fast measurement. So most of other 2D materials at the moment, they are using or they are exfoliated on the wafer, so you have some kind of transfer process. So in our case, we can deposit these 2D materials on a full 8-inch wafer. So this is shown here. So here it was MOS2, and here you can see from the resistivity measurement that, okay, beside of the part on the bottom side, that we have a really homogeneous deposition of these 2D material. So here there are also ongoing research activities. So I mean, it's on one hand, we can deposit it, but if we have deposited on a full wafer, then the next step is that you want to structure it. And this is not as easy. So here are our ongoing research processes to establish litho processes and also etching these materials. These materials were used in again in a gas sensor. It was a resistive gas sensor, and the specialty here was that we do not use rigid silicon wafers, but that we used a flexible foil for this. Yeah, because of the high conformity, ALD could also be used for encapsulation sensors. So the requirements here are that they are hermetically closed. In case of implantable or of medical devices, they need to be biocompatible, consistent against chemicals and humidity. If you have some membrane, for example, you need a low mechanical influence. In some cases, also protection against light could be useful, and also the protection against harsh environments, so for example, against corrosive gases. So here, for these applications, we're normally using not just one material, but we are using nanolaminates out of several materials to combine the benefits of of two or more materials. We also have the possibility for surface modification, so for adjustment of the hydrophilicity by using the ALD layers. So in this case, it was used for a lab-on-chip application to get a better, so that the drops of a fluid could fluidic better on the chip to get, in this case, it was for cell sorting system. Okay, now I come to my conclusion. So in our institute, we can cover the full process chain, and if there are any process steps which are not available in our institute, then we have our partner institutes out of the FMD. We could be your partner for developing and also for upscaling your process up to around a few hundred or up to 1,000 wafers per year. We have a professional 200 millimeter clean room here for small and medium-sized production. So, and if you're interested, or if there are any questions, please contact me or visit us in our booth 156. Okay. Thank you for your attention. And are there any questions?